In 1977, a spacecraft left Earth on a trajectory no human being alive today will see completed. It is now so far away that a signal from it takes more than 23 hours to reach Earth, and the Sun, from where Voyager 1 sits, looks like nothing more than a slightly brighter star. Every day it sends a signal home. Every day, engineers here on Earth sit down and read it. The distance between those two facts is where the extraordinary quietly waits. Tonight, we will trace every link in that chain, from the nuclear heart of Voyager itself to the listening dishes on 3 continents, and understand how an impossible conversation stays alive. Before we dive in, if you love exploring deep space as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. The textbook answer to how we remain in contact with Voyager 1 is elegant in its simplicity. Radio waves travel at the speed of light. The spacecraft has a transmitter. The transmitter generates a signal. That signal crosses space, arrives at a dish on the ground, and the dish reads it. Simple, bounded, complete. If you found that answer satisfying, that is entirely understandable. It is technically accurate in the same way that describing a human body as bones surrounded by tissue is technically accurate, correct at the surface, silent about everything that actually matters. But here's what almost nobody tells you about that simple picture. The moment you put real numbers into it, the entire picture collapses. Voyager 1 is currently more than 25 billion kilometers from Earth, traveling through interstellar space. Its transmitter broadcasts its signal homeward, using 22 watts of power, roughly equivalent to a dim incandescent bulb, the kind you might find in an older desk lamp that barely lights a corner of a room. That signal expands outward in all directions as it travels, thinning according to a law of physics that makes no exceptions for human ambition. The inverse square law, meaning that the intensity of any radiated wave decreases in proportion to the square of the distance traveled, is relentless and absolute. Double the distance and the signal's power falls to 1/4. Triple the distance and it drops to 1/9. At 25 billion kilometers, a 22-watt signal that began at the transmitter has spread across a sphere so enormously vast that the fraction intercepted by even the largest receiving dish on Earth is nearly unmeasurable. The only reason we still have contact is that the Deep Space Network's 70-meter dishes can detect signals measured in billionths of a billionth of a watt. And we read every bit of it. That gap between the whisper that leaves the spacecraft and the coherent data that engineers extract from it on the ground is the heart of what this story is actually about. It is not simply a matter of large dishes and sensitive electronics, though both of those things are essential parts of it. It is a layered achievement reaching back through nearly 50 years of decisions, adaptations, inventive solutions, and near disasters. And it is, even now as these words reach you, operating at the very edge of what physics allows. Before we can trace that achievement from its beginning to its present moment, we need to understand what Voyager 1 actually is. Not as a cultural object, not as a symbol of human ambition projected into the void. As a machine with specific physical components, real constraints, and a power supply that has been running down for the better part of 5 decades. The main body of Voyager 1, the central bus, is a 10-sided aluminum framework roughly 47 centimeters across. Inside it live the 3 onboard computers, the power distribution systems, and the electronics that manage all spacecraft functions. From this central body, a series of booms extends outward into the cold, one supporting the science instruments, a second carrying the 3 radioisotope thermoelectric generators that provide all the spacecraft's power, and a third extending the magnetometer far enough from the main body that the generator's own faint electromagnetic fields cannot contaminate its measurements. Rising from the center of the structure is the high-gain antenna, a precisely shaped dish 3.7 meters in diameter, a Cassegrain design built to collect and focus radio energy with maximal efficiency. That antenna is Voyager's one sustained connection to the planet that built it. Everything the spacecraft has ever communicated, every image of Jupiter's storms, every reading from Saturn's rings, every measurement from the boundary of the solar system, has passed through that dish and across the void between worlds. The entire spacecraft weighed about 815 kilograms at launch, and after decades of thruster use, now weighs roughly 733 kilograms. In any given parking lot, it would occupy a single space without drama. There is nothing visually imposing about its dimensions. What makes Voyager 1 extraordinary is not how large it is, but where it is, and the implications of that location for every system on board. The spacecraft was designed to carry 11 science instruments. Most of them have now been switched off, one by one, as the years accumulated and the energy supply narrowed. As of April 2026, after the shutdown of the low-energy charged particle experiment, only 2 instruments remain in operation on Voyager 1. The plasma wave subsystem, which detects oscillations in the charged particles of interstellar space, and the magnetometer, which measures the magnetic fields threading that same environment. Everything else, the cameras that returned those first close views of Jupiter's moons, the ultraviolet spectrometer, the infrared radiometer, the photopolarimeter, has been powered down, each shutdown a quiet concession to a shrinking energy budget that no engineer can reverse. The onboard computers present their own kind of revelation. Voyager 1 runs on 3 separate computer systems, each with a distinct function. The flight data subsystem collects data from the science instruments and packages it for transmission. The computer command system receives and executes commands sent from Earth, and the attitude and articulation control system manages the spacecraft's orientation. Together, these 3 computers manage an object traveling at roughly 61,000 kilometers per hour, about 17 kilometers per second, through the interstellar medium. Together, they store a combined memory of just 69.63 kilobytes. 69.63 kilobytes. A single uncompressed photograph from a modern smartphone contains tens of thousands of times more data. A single second of audio recorded at standard quality contains many multiples of what Voyager's entire computing memory can hold. The spacecraft that has traveled further than any human-made object in history runs on less onboard memory than early personal computers sold in department stores in the mid-1980s. This was not a failure of imagination. It was a triumph of constrained design. Every byte accounted for, every instruction deliberate, a system optimized not for capacity, but for longevity in an environment where no repair crew would ever arrive. The engineers who built Voyager, one could not predict every scenario the spacecraft would encounter over 50 years in space. So they built redundancy where they could, simplicity where they had to, and they trusted the design to hold. That trust, as we will discover, has been tested in ways its architects could not have foreseen. To understand why this machine exists at all, and why it was designed the way it was, you need to go back to a planetary alignment that happens once every 176 years. In the mid-1960s, a young aerospace engineer named Gary Flandreau, working at JPL in Pasadena, California, was conducting trajectory studies for potential outer planet missions when he recognized something remarkable in his calculations. Jupiter, Saturn, Uranus, and Neptune were converging toward a rare orbital configuration, one in which a spacecraft, using the gravitational pull of each planet as a natural slingshot, could visit all four in a single continuous journey. The technique is called gravitational assist. By flying close to a massive body and using that body's own orbital velocity and gravity to bend and accelerate a spacecraft's trajectory, engineers can add enormous speed without burning additional fuel. In theory, it had been known for decades. In practice, it had barely been proven. What Flandreau's 1965 calculations showed was that the alignment was coming, that the launch window was narrow. It would open in 1977 and close within a few years, and that it would not return within the lifetime of anyone working in the space program at that time. The window was real, and NASA intended to use it. 2 spacecraft were designed and built at JPL over the following years. Originally, their mission profiles were ambitious enough to encompass all 4 outer planets and more. Budget pressures trimmed those ambitions. Voyager 1's mission was ultimately shaped around a close flyby of Titan, Saturn's largest moon, which was known to have a substantial atmosphere and was considered one of the most scientifically important targets in the outer solar system. Voyager 2 was launched first. Voyager 1 launched 16 days later, on September 5, 1977. Despite launching second, Voyager 1 was placed on a faster, more direct trajectory to Jupiter and overtook its twin within months of launch. Both spacecraft were initially designed to last 5 years. 5 years was considered an optimistic but credible goal in 1977. There was no serious plan at the program's outset for what either spacecraft would do after that. The assumption, reasonable by the standards of any previous mission, was that they would eventually fall silent, that something would fail, that the cold and the radiation and the sheer duration would win. They are still transmitting. The mission's project scientist was Edward Stone, who joined the Voyager team at JPL in 1972, 5 years before either spacecraft left the ground. Stone, who was born in 1936 and died in 2024, remained associated with the Voyager program for more than 50 years, longer than any other scientist in the history of crewed or robotic space exploration. He was present for the Jupiter encounters and the Saturn encounters. He was present for Voyager 2's visits to Uranus and Neptune. He was present for the first scientific measurements that suggested Voyager 1 was approaching the heliopause, the boundary between the solar system and interstellar space. And he was present when, in 2012, that boundary was crossed. His career was, in some profound sense, coextensive with the mission itself. Voyager 1 reached Jupiter in March 1979. The encounter rewrote what we thought we understood about the outer solar system. The images returned showed Jupiter as a world of violent, living complexity, storm systems of extraordinary scale, a thin ring that no pre-mission model had predicted, and most astonishing of all, active volcanic eruptions on the surface of Io, the innermost of Jupiter's large moons, making it the first body in the solar system besides Earth confirmed to have ongoing geological activity. Europa, the next moon outward, showed surface patterns suggesting, though not yet proving, a liquid ocean sealed beneath its fractured ice shell. Voyager 1 did not linger. The gravitational assist from Jupiter bent its trajectory and accelerated it towards Saturn, which it reached in November 1980. The Saturn encounter was dominated by the mission's commitment to Titan. That flyby returned the first detailed data on Titan's atmosphere, confirming it as nitrogen-rich and thicker at the surface than Earth's own air, hinting at the possibility of liquid hydrocarbons pooling on its surface in place of water. It was spectacularly successful, and it permanently determined the spacecraft's future. The trajectory required for the Titan flyby sent Voyager 1 downward through Saturn's orbital plane, then upward, bending its path out of the ecliptic, the flat disk in which the planets orbit, at an angle that made any further planetary encounter impossible. After Saturn, the spacecraft was pointed at nothing. No Uranus, no Neptune, no Pluto on the distant horizon. After Saturn, there was only the void, and it went into the void anyway. It kept going through the 1980s as its signal took progressively longer to arrive. It kept going through the 1990s as its trajectory carried it past the orbits of the planets it would never visit. It kept going into the 2000s, through the Helios sheath, the turbulent outermost region of the Sun's influence, where the solar wind slows and piles up against the pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. And on August 25th, 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, becoming the first spacecraft to enter interstellar space. The heliopause is not a wall with a surface you can see. It is a pressure boundary, a region where two competing environments finally reach an equilibrium and one gives way to the other. But the instruments on board registered the crossing unmistakably. The density of charged particles shifted. The character of the magnetic field changed. The plasma environment around the spacecraft was suddenly, definitively different from anything the solar wind had ever produced. Voyager 1 was in the interstellar medium, in the space between the stars. It did not stop there. It has not stopped. It has never stopped. Pause here for a moment and take stock of where we are. Voyager 1 sits at a distance of approximately 172 astronomical units from Earth, 25.8 billion kilometers, moving outward at 17 kilometers per second. As of 2025, signals from Voyager 1 took more than 23 hours to reach Earth. The spacecraft is projected to cross the one light-day boundary, the point at which a signal traveling at the speed of light will take a full 24 hours to reach it, in November 2026. As of this moment, two of its instruments still function. As of this moment, engineers at tracking stations spread across 3 continents are still listening. The question is what that listening actually requires. To answer it, we begin at the very beginning of the signal chain, not at the transmitter, not at the antenna, but further back than that. We begin where the energy itself originates. We begin with atoms. Voyager 1 has 3 radioisotope thermoelectric generators mounted on a boom extending from its main body. Each one contains 24 pressed plutonium, 238 oxide spheres. These spheres, each about the size of a golf ball, though considerably denser and far more energetic, are the power source for everything. They are the reason the transmitter runs. They are the reason the computers function. They are the reason that, 48 years after launch, there is still a signal to receive. Plutonium-238 decays naturally, shedding alpha particles as its nuclei release mass and energy. That released energy manifests as heat. The RTGs, radioisotope thermoelectric generators, which in plain English means nuclear batteries that convert radioactive heat into electricity, are designed to capture that heat and channel it into a usable electrical current through a phenomenon called the Seebeck effect. The Seebeck effect was identified in 1821 by the German physicist Thomas Johann Seebeck, who discovered that a circuit made of two dissimilar conducting materials will generate an electrical current whenever one junction of those materials is held at a higher temperature than the other. Heat on one side, cold on the other, and electricity flows between them. No moving parts, no combustion, no mechanism to wear out in the traditional sense. Each of Voyager's RTGs contains 312 silicon-germanium thermoelectric couples. 312 of these heat-to-current junctions, stacked and arranged to maximize the electrical output from the temperature gradient between the hot plutonium interior and the cold face radiating waste heat into the vacuum of space. The hot end runs at approximately 1000 degrees Celsius, fed directly by the decaying plutonium. The cold end sits at around 300 degrees Celsius, radiating waste heat through external fins. The temperature differential pushes electrons across the junctions, producing about 157 watts of electrical power per generator at the start of the mission. Across all three RTGs, roughly 470 watts of electricity at launch. 470 watts. Enough to power a modest desktop computer. Enough to keep lights burning in a small room. Enough, crucially, to run a suite of scientific instruments and a transmitter and 3 computers and a set of attitude control thrusters on a spacecraft moving through the interstellar medium. But that power has not remained constant. The power output of the RTGs declines over time due to the 87.7-year half-life of the plutonium-238 fuel and the degradation of the thermocouples. The silicon-germanium thermocouples lose efficiency as their crystal structure changes under prolonged high-temperature operation, a process that no engineering solution has yet been able to prevent or reverse. The combined effect of fuel decay and thermocouple degradation strips approximately 4 watts of electrical output from the spacecraft every year. 4 watts per year does not sound catastrophic, but compound it over nearly 5 decades, and the arithmetic becomes sobering. After decades of operation, each spacecraft now produces less than half its original electrical power, leaving engineers with razor-thin margins between keeping the radio alive and tripping the undervoltage fault protection system. The spacecraft that launched with 470 watts of available electricity now runs on a fraction of that, a budget so constrained, so carefully managed, that every instrument shutdown must be weighed against the risk of losing the one system that justifies all the others: the radio transmitter. As the aging Voyager probes continue exploring the cosmos, the team has slowly turned off instruments to conserve power and extend the missions. Camera systems, off. Spectrometers, off. Heaters that once kept sensitive instruments within their operating temperature range, off. One by one, the engineers accepted that an instrument running cold might still function, while an instrument with no power cannot function at all. Each decision has been made deliberately, in consultation with the scientific community, each one representing the permanent loss of some measurement that could never be taken again. What remains is the radio. 2 instruments and 1 transmitter, sustained by the decaying warmth of 13.5 kilograms of plutonium, sealed within 3 cylinders on a boom, moving through the coldest, emptiest environment our species has ever visited. This is the foundation on which the rest of the story rests. This is where the signal begins. The chain starts with heat and ends with meaning. Between the radioisotope thermoelectric generators and the data that appears on a screen at JPL, there are several more links in the causal sequence, each essential, each operating at tolerances that leave almost no room for error. The electrical power produced by the RTGs flows through the spacecraft's power distribution systems to the radio transmitter. Voyager carries 2 transmitters, primary and backup. but the primary has carried nearly every transmission since launch. The transmitter's function is to convert electrical energy into radio frequency energy, electromagnetic waves that propagate through the vacuum of space at the speed of light. Voyager 1 normally transmits data to Earth on the X-band frequency of 8.4 GHz, while signals sent from Earth to Voyager travel at roughly 2.1 GHz in the S-band. Voyager carries a backup S-band downlink at 2.3 GHz, but it has not been used routinely since the last planetary encounter. X-band at 8.4 GHz means 8.4 billion complete wave oscillations per second. The wave cycles so fast that no human sense or ordinary instrument could perceive it directly. But it carries information as reliably as any medium we know, provided something on the receiving end is sensitive enough to read it. That, provided, is doing tremendous work, and we will arrive at it soon. The transmitter's output is 22 watts, not 22 kilowatts, not 22 megawatts. 22 watts pressed into a frequency and sent toward the high-gain antenna, where it will be shaped into the narrowest possible beam before departing into space. The high-gain antenna is not an amplifier. It does not add energy to the signal. What it does is concentrate the energy that already exists. A parabolic dish, when transmitting, focuses the outgoing signal along its axis, rather than allowing it to radiate equally in all directions. The technical term for this focusing is gain, the ratio of the antenna's directed power in a given direction to the power that would have been produced by a non-directional source using the same total energy. The 3.7-meter high-gain Cassegrain antenna sends and receives radio waves via the 3 deep space network stations on Earth. Without it, Voyager's 22-watt signal would spread uniformly in all directions and become effectively undetectable within a vanishingly small fraction of its current distance. The plutonium-238 at the heart of those generators was first synthesized in December 1940 by physicist Glenn Seaborg and his colleagues, who created it by bombarding uranium-238 with deuterons in a particle accelerator. Seaborg was working in the context of early nuclear physics, not spacecraft propulsion. But the isotope his team created, with its 87.7-year half-life and its steady, manageable alpha decay, turned out to be almost ideally suited for a purpose no one in 1940 could have anticipated. The principle of converting its decay heat into electricity was first demonstrated as a working device in 1954, when engineers Ken Jordan and John Burden at the Mound Laboratory in Ohio built the first functional RTG, a nuclear battery with no moving parts and a power output that would last for decades. From that 1954 laboratory demonstration to the 3 canisters mounted on a boom in interstellar space, the chain is direct and unbroken. But even with the antenna's directional concentration, one more prerequisite must be met before any of the rest of the chain can function. The antenna must be pointed at Earth. At 25 billion kilometers, Earth is not simply distant. It is for all practical purposes invisible. From Voyager's position in interstellar space, the Sun is a bright star. Earth is an unresolvable dot orbiting that star, detectable not by eye or by Voyager's remaining instruments, but only by precise mathematical calculation. And yet, the high-gain antenna must be aimed at Earth with sufficient accuracy that the transmitted beam actually intersects the planet, rather than missing it by millions of kilometers. This pointing is managed by the Attitude and Articulation Control System, the onboard computer that fires small hydrazine thrusters to adjust and maintain the spacecraft's orientation. The system uses reference points, sun sensors, and a star tracker locked onto the bright star Canopus, roughly 310 light-years from Earth and visible as one of the brightest objects in the southern sky, to calculate the spacecraft's orientation and make the continuous fine adjustments required to keep the antenna correctly aimed. The thrusters have been degrading for decades. In 2017, Voyager 1's primary thrusters showed signs of degradation, so engineers switched to another set of thrusters that had originally been used during the spacecraft's planetary encounters. Those thrusters worked, despite having been unused for 37 years. In September 2024, NASA performed another thruster swap, switching from a clogged set of thrusters to less clogged ones that had not been used since 2018. The spacecraft no longer has a backup available for its thruster system, and everything on board is single string, according to Suzanne Dodd, Voyager project manager at JPL Single String. In engineering, that phrase means there is no redundancy left, no spare time, no fallback. If the last remaining functional attitude control thrusters fail, the antenna will drift away from Earth and the signal will stop arriving. Not because the spacecraft has stopped transmitting, but because what it transmits will no longer be aimed at anything. For now, the pointing holds. The thrusters fire their small pulses. The conversation continues. The signal leaves the spacecraft. This is the moment where the chain crosses from human engineering into pure physics. From this point forward, there are no engineers who can intervene, no redundant systems to activate, no decisions left to make. The signal is alone in space, a propagating electromagnetic wave, and the rules governing it are fixed and ancient and entirely indifferent to what the engineers who built the transmitter would prefer. Picture yourself at the instant of transmission, the precise moment when the electrical oscillations in Voyager's transmitter are converted into an outward propagating wave. For one instant, the signal exists at the source, at full strength, concentrated by the antenna and aimed at a planet it cannot see. Then it is gone. It expands outward, spherically, into the interstellar medium. It will not refocus. It will not be compressed or redirected. It will arrive at Earth 23 hours and more later, having spread across a sphere of unimaginable scale, and whatever fraction of that sphere intersects a receiving dish on the ground is all that will ever be recovered. The speed at which this signal travels is 299,792 kilometers per second. That is the speed of light in a vacuum, and radio waves are light, electromagnetic radiation at the low-frequency end of the spectrum, but light nonetheless. At that speed, the signal covers the distance from the Earth to the Moon in 1.3 seconds. It crosses the distance from Earth to the Sun, 150 million kilometers, in approximately 8 minutes and 20 seconds. As of 2025, signals from Voyager 1 took more than 23 hours to reach Earth. And in late 2026, Voyager 1 will cross the line where a signal from it will take 24 hours to reach us, the one light day milestone. Pause here and sit with that number. Not the distance in kilometers, the time. More than 23 hours at the speed of light. Light, which circles the Earth 7 times in a single second, takes a full working day to reach Voyager. The Earth completes a full rotation while that signal is in transit. The sun rises, arcs across the sky, sets, and has been below the horizon for hours. And the signal is still traveling, and that is only in one direction. The round trip, a command sent from Earth, plus waiting time, plus the return confirmation, takes nearly 2 full days. Consider what that means for the people who operate the mission. Once the coding fix for the probe's engineering data was finished, the team had to wait 22.5 hours for the signal to reach the probe, and then another 22.5 hours for the signal to return to Earth. Every decision made in mission control is a decision made across a communication delay measured in days. Every command is an act of faith, sent into the void, with nearly 2 full rotations of the Earth between the sending and the knowing. At Jupiter, the spacecraft could transmit data at 115.2 kilobits per second. Today, its data channel runs at just 160 bits per second, the rate at which all telemetry, both engineering and science data, now returns to Earth. 160 bits per second, the current rate of Voyager's data channel. That number deserves its own paragraph, because it is so far removed from the data rates that define modern experience that it resists intuitive comparison. Your phone, reading this sentence, is capable of transmitting and receiving data at rates millions of times faster. A modern home internet connection moves more data in a single second than Voyager transmits in an entire day. And the reason for this is not that Voyager's engineers made poor design choices in 1977. The reason is the inverse square law. Here is how mathematics works. When Voyager 1 passed Jupiter in 1979, it was approximately 630 million kilometers from Earth. It is now roughly 25 billion kilometers away, approximately 40 times further. The inverse square law states that the received signal power decreases as the square of the distance. 40 squared is 1,600. So the signal that was already stretched to near its detectable limit at Jupiter arrives today with roughly 1,600 times less power even than it had then. The usable data rate has been reduced accordingly, reduced again, reduced once more. Each reduction a negotiated settlement with physics that the spacecraft's designers could anticipate but could not prevent. Voyager's data channel now runs at 160 bits per second, 20 bytes per second, 20 characters of text per second in the simplest encoding. At that rate, the contents of a standard newspaper article would take hours to arrive. The complete measurements from a single instrument pass over a feature of scientific interest might take days to transmit. The spacecraft is moving through the most scientifically novel environment in human history, the interstellar medium between the stars, and it can report what it finds only in a thin trickle. Its data rates a tiny fraction of anything in modern experience. It had been 22 watts at the transmitter. It had been focused by 3.7 meters of precision machined aluminum. It had been aimed at a planet it could not see. Now it was alone and diminishing. The information itself is encoded onto the carrier wave using a technique called binary phase shift keying. Phase shift keying, in plain English, means that the data is carried not in the amplitude or frequency of the wave, but in its phase, its timing relationship to a reference oscillation. A shift in phase by 180 degrees represents one binary state. No shift represents the other. Ones and zeros are encoded as patterns of these phase transitions, and the receiving system on the ground must reconstruct the data by measuring those transitions against a locally generated reference signal. This method is robust against variations in signal strength. The phase information survives even when the amplitude has been diminished to near nothingness. And it is precisely this robustness that makes it the right choice for a signal arriving from 25 billion kilometers away. The signal also carries error-correcting codes embedded in the data stream. At 40 bits per second across a 23-hour light travel time, requesting a retransmission of corrupted data is not practical. The error-correcting codes allow the ground system to identify likely errors and reconstruct the intended data mathematically without any further communication with the spacecraft. These codes impose an overhead cost. Some of those 40 bits per second are consumed by the error correction structure rather than by science data. But they are not optional. Without them, the signal would be unreadable. The signal passes through the interstellar medium on its way to Earth, and the interstellar medium is not empty. It is a dilute, partially ionized plasma, containing both neutral atoms, mostly hydrogen and helium, and free electrons, threading through weak magnetic fields at densities so low that a cubic centimeter of it might contain, on average, only a fraction of an atom of matter. By terrestrial standards, this is a better vacuum than anything engineers can produce in a laboratory. But it is not nothing, and a radio wave traveling through it for 23 hours is affected by it in measurable ways. The charged particles of the interstellar medium cause the signal to scintillate, to vary slightly in apparent intensity as the wave diffracts through the irregular density structure of the plasma, similar in principle to the way starlight twinkles as it passes through Earth's turbulent atmosphere. This effect is small enough to be manageable at Voyager's operating frequencies. But it is precisely measurable, and it has become a source of scientific information in its own right. Stella Ocker, a postdoctoral fellow at Caltech and the Carnegie Observatories, has noted that it is surprisingly difficult to observe the interstellar medium that is just outside of our heliosphere. And Voyager 1's signal, traveling through it for 23 hours, provides a form of measurement no other instrument can replicate. The signal's propagation characteristics encode information about the medium it passed through. The reception of the signal is simultaneously science. We cannot know with full certainty precisely how the interstellar medium varies across the path the signal has traveled. Its structure is irregular, its composition differs from place to place, and the instruments sensitive enough to probe it directly are the same instruments that depend on the signal arriving correctly. Some uncertainty about what the signal encounters during transit is, at this distance, irreducible. The signal arrives at Earth, still oscillating at 8.4 gigahertz, still encoding its data in phase transitions, still carrying its error-correcting codes, having crossed 25 billion kilometers of space and plasma and magnetic field. The only reason we still have contact is that the Deep Space Network's 70-meter dishes can detect signals measured in billionths of a watt. The chain has not broken yet. But what comes next is where the conversation's survival becomes most improbable. Take stock of where we are. The signal has left Voyager 1 and traveled for more than 23 hours at the speed of light. It has passed through the interstellar medium and the outer heliosphere and the inner solar system, fading with each meter of its journey according to a law that has no exceptions. It is now arriving at the upper atmosphere of Earth, thinned to near nothingness, a whisper in a sea of electromagnetic background noise. 3 places on this planet are prepared to receive it. The Deep Space Network formally announced its intention to support missions into deep space on Christmas Eve 1963. In the more than 6 decades since that announcement, it has supported every major NASA interplanetary mission: Pioneer, Mariner, Viking, Voyager, Galileo, Cassini, New Horizons, Mars exploration rovers, Perseverance, and dozens more. It received the first images of Mars's surface from Mariner 4. It received Neil Armstrong's words from the lunar surface in 1969. It maintained contact with the Cassini spacecraft through 13 years orbiting Saturn. And every day, without interruption, it listens for the 2 faintest engineered signals in the human world. The 3 communication complexes are spaced roughly 120 degrees apart around the globe: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. As the Earth rotates, at least one site is always in view of any given deep space target. The geometry of this arrangement is not incidental. It is the essential design principle. No single station could maintain continuous contact with a deep space object, because the Earth's rotation would carry it below the horizon every several hours. 3 stations arranged at 120-degree intervals ensure that as one falls below the horizon, the next has already risen to take its place. Hand off, hand off, hand off. A 24-hour relay race that has been running since 1963. Goldstone sits in the Mojave Desert, approximately 60 kilometers north of Barstow, California, in a dry valley chosen for its radio quietness, far from the electromagnetic interference of cities, at an elevation that reduces the column of water vapor above the dishes and improves the clarity of the received signal. Madrid is located in Robledo de Chavela, in the hills west of the Spanish capital, at a similar distance from urban noise sources. Canberra occupies a rolling country in the Australian Capital Territory, positioned to cover the southern hemisphere of the sky and to maintain access to spacecraft whose trajectories carry them south of the celestial equator. Each complex hosts multiple antennas. The workhorse instruments are the 34-meter beam waveguide dishes, modern and reliable, capable of supporting the great majority of deep space missions. But for Voyager 1, the 34-meter dishes are not sufficient. The signal is too faint, the distance too great. Voyager requires the largest antennas on the planet. The textbook answer to the question of how you receive a fainter and fainter signal is straightforward. You build a larger dish. A larger dish intercepts more of the incoming signal. More collected signals means better signal-to-noise ratio. The math is clear, the solution seems obvious, and it scales. Twice the diameter means 4 times the collecting area and 4 times the collected power. But here's what almost nobody tells you. That picture is true as far as it goes and stops short before it reaches the genuinely difficult problem. The collecting area of a dish is not the only constraint on its sensitivity. At the signal levels involved in receiving Voyager, the limiting factor is not the size of the dish. It is the noise floor of the receiving electronics themselves, and the fundamental thermodynamic limits that no dish size can overcome. The larger dish answer also runs into structural engineering constraints that arrive well before you reach the scale you would actually want, and pointing accuracy requirements that become increasingly severe as the dish grows. The 3 70-meter DSSS, DSS-14, DSS-43, and DSS-63 were originally built as 64-meter diameter antennas. The first, DSS-14, began operation in 1966. All 3 were expanded from 64 meters to 70 meters in diameter between 1986 and 1988, specifically to increase their sensitivity to support Voyager 2's encounter with Neptune. The expansion of those dishes was not a modest upgrade. Each antenna's main reflector, a precision-machined parabola spanning 70 meters from edge to edge, had to be physically reconstructed to its new diameter while maintaining the surface accuracy required for operation at microwave frequencies. A surface that is locally imprecise by even a few millimeters across a 70-meter span will degrade the antenna's focusing performance significantly. The replacement panels had to be shaped to a tolerance measured in fractions of a millimeter, installed across a structure that weighs millions of pounds, sitting outdoors in weather that includes wind, thermal expansion, and the slow gravitational sag of metal under its own weight. Each 70-meter antenna has 6 million pounds of moving structure. When that structure needs to track a moving target across the sky, it must rotate and tilt with continuous smooth motion. no vibrations, no jerks, no flexure in the reflector surface that would distort its focus. The solution is a hydrostatic azimuth bearing. The entire dish floats on a thin film of pressurized oil as it rotates, allowing 6 million pounds to move with almost no friction and almost no vibration, the metal never touching metal. The bearing must be maintained and replenished continuously. It represents an engineering solution to a problem that most people would not think to ask. How do you smoothly rotate something that weighs as much as several hundred family cars? DSS-43 at Canberra was brought online in December 1972, 5 years before either Voyager launched. The gap between DSS-43's capabilities and other antennas widened in 1987, when DSS-43 was equipped with a 70-meter dish in anticipation of Voyager 2's 1989 encounter with the planet Neptune. DSS-43 boasts a pointing accuracy of 0.005 degrees, 18 arc-seconds, which is important for ensuring that it is pointed directly at a distant spacecraft. The antenna has a transmitter capable of 400 kilowatts. 400 kilowatts is the power sent from Earth when a command must reach Voyager. The spacecraft responds with 22 watts. The asymmetry is extreme. Earth shouts, Voyager whispers. And even so, the whisper at the receiving end is almost too faint to hear. DSS-43 received Apollo 17's transmissions from the lunar surface in December 1972, the very month it came online. It tracked Pioneer 10 as that spacecraft crossed the outer solar system. It received the first data from Voyager 2 after its Neptune encounter in 1989. It has been one of the primary ears of the human conversation with the outer solar system ever since. And it holds a distinction that makes it operationally irreplaceable. As of 2025, both Voyager 1 and Voyager 2 can only receive uplink commands from Canberra's DSS-43. Voyager 1 still sends its downlink data to Goldstone and Madrid, but for sending commands, Canberra is the only dish that can reach it. This means that DSS-43 is not merely the best option for communicating with Voyager 2. It is the only option. And that matters for what happened in 2020. When DSS-43 in Canberra went down for upgrades in 2020, NASA could not send commands to Voyager 2 for 11 months. The spacecraft operated autonomously, executing its last uploaded instructions, waiting. Engineers could still receive data from the spacecraft. The smaller 34-meter dishes at the Canberra complex can collect the downlink signal, but they could not send anything back. For 11 months, Voyager 2 was a correspondent from whom you could receive letters, but to whom you could not reply. It completed its assigned operations faithfully in silence. The dish came back online in February 2021. Once the updates were completed, test commands were sent to Voyager 2. After about 37 hours, DSS-43 received a response from the space probe confirming it had received the call. Between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the only antenna capable of sending commands to Voyager 1 and 2, was offline for major upgrades, with only limited operational windows in August and December 2025. And separately, in a development that barely registered in the broader public consciousness, DSS-14, the Mars antenna at Goldstone, the network's oldest and historically most storied 70-meter dish, went offline in September 2025 for its own major refurbishment. For stretches of late 2025, 2 of the 3 70-meter uplink antennas on Earth were simultaneously unavailable. These are not redundant assets. For the hardest jobs, each 70-meter dish is effectively a single point of failure for an entire hemisphere. The communication chain that keeps Voyager alive had, for a period, narrowed to a single dish on a single continent. It is worth sitting with that image. One dish, one continent. The only physical infrastructure on Earth capable of maintaining the conversation with the most distant human-made object in existence. The chain held. The dishes came back online. The conversation resumed. But the fragility it exposed is not going away. Now we arrive at the moment when the signal actually enters the receiving equipment, and at the problem that makes this step perhaps more physically challenging than any other in the chain. Picture yourself at the Goldstone complex on a clear winter night, when Voyager 1 is positioned above the western horizon and DSS-14 is tracking it slowly across the sky. The dish is moving, its rotation imperceptible unless you look for a long time, following the spacecraft's position with a precision measured in arc seconds. At the dish's focal point, a receiver is housed in a cryogenic dewar, kept at temperatures approaching absolute zero, shielded from the thermal noise of the surrounding environment. The signal arriving at that receiver has crossed 25 billion kilometers. And the question that makes this entire endeavor extraordinary, is how do you detect something carrying billionths of a watt? This is not primarily a question of engineering sophistication. It is a question of physics, and specifically of thermodynamics. Every physical object above absolute zero temperature radiates electromagnetic noise. The atoms in any material are in constant thermal motion, and that thermal agitation generates random electrical fluctuations across any conducting medium. This phenomenon, described quantitatively in the late 1920s by physicists John Johnson and Harry Nyquist, working at Bell Telephone Laboratories, produces what is called thermal noise or Johnson-Nyquist noise. The noise power it generates is proportional to the temperature of the material and to the bandwidth of the system observing it. In plain English, warmer electronics make more noise, and broader bandwidth means more noise power in the observation window. The thermal noise problem at these signal levels is severe. At room temperature, the thermal noise produced by the amplifier circuits in a receiving system overwhelms Voyager's signal by many orders of magnitude. The spacecraft's transmission arrives as a pattern buried so far beneath the random electrical fluctuations of a room temperature receiver that no processing algorithm could extract it. The signal is there. It is real. It carries data. But it cannot be seen through the noise wall that room temperature erects around the receiver. The solution is cold. The receiving electronics at each DSN station are cooled to temperatures of approximately 15 to 20 degrees above absolute zero, about negative 255 to 260 degrees Celsius. At these cryogenic temperatures, the thermal motion of the atoms in the amplifier components is suppressed to the point where their noise contribution becomes small enough for Voyager's signal to stand above it. Not comfortably, not with large margins, but above it. The cryogenic dewars that maintain these temperatures must operate continuously, must never fail, must be serviced on a schedule that does not allow the temperature to rise. If the cryogenic system warms, the noise floor rises with it, and the signal disappears. The first amplification stage, the low-noise amplifier, must add as little noise of its own as possible while boosting the signal by many orders of magnitude. Any noise added by the amplifier itself is indistinguishable from signal and cannot later be removed. The entire amplification chain is a long, careful accumulation of signal that simultaneously and irreversibly accumulates noise, and the final signal-to-noise ratio depends on how much noise was introduced at each step. The DSN's engineers have spent decades optimizing both the amplifier design and the cryogenic systems to push that ratio as high as physics allows. Once amplified, the signal enters the digital processing chain. The carrier wave, the 8.4 GHz oscillation, must be separated from the data it carries. A phase-locked loop tracks the carrier's precise frequency and phase, locking onto the incoming wave and following it even as its frequency shifts slightly due to the Doppler effect. Those Doppler shifts are a source of scientific information in their own right. By measuring how the frequency of Voyager's signal changes as the spacecraft moves relative to Earth, engineers can calculate the spacecraft's velocity with extraordinary precision, detecting any gravitational influences on its trajectory with an accuracy that was itself unexpected when Voyager was first launched. The data stream, the binary ones and zeros encoded in the phase transitions, is extracted from the carrier and passed to the error-correcting systems. Some fraction of the bits will have been flipped by noise in the receiving chain or during propagation. The mathematical structure of the error-correcting codes identifies the likely errors and corrects them, producing a clean binary stream that represents the actual telemetry from Voyager's instruments. The signal arrives. It is amplified. It is separated from the noise. It is phase-tracked. It is decoded. It is corrected. And at the end of that sequence, somewhere in the signal processing center at Goldstone, or in Madrid's high desert station at Robledo de Chavela, or in the rolling hills outside Canberra, a number appears on a screen. A number measured by a magnetometer in interstellar space, 25 billion kilometers away. The full chain: plutonium decay, thermoelectric conversion, electrical power, radio frequency generation, antenna concentration, electromagnetic propagation, inverse square attenuation, interstellar medium interaction, cryogenic reception, low noise amplification, phase-locked decoding, error correction, display. Every link present, every link necessary, every link aging. This is how the conversation is maintained, and it has been maintained this way under increasing stress for nearly 50 years. But the chain has broken before, and when it broke, the way it was repaired was unlike anything in the history of spacecraft operations. That is where we turn next. On November 14th, 2023, Voyager 1 stopped making sense. The spacecraft stopped sending readable science and engineering data back to Earth on November 14th, 2023. Even though mission controllers could tell the spacecraft was still receiving their commands and otherwise operating normally. The radio signal from Voyager was present and steady, arriving at the Deep Space Network antennas on schedule, carrying the regular pulse of a transmitter that had been broadcasting without meaningful interruption for 46 years. But the data encoded in that signal, the telemetry that should have reported on the spacecraft's health, its orientation, the readings from its remaining instruments, had become noise. The Flight Data System's telemetry modulation unit began sending an indecipherable repeating pattern of code. Voyager 1's Flight Data System had been stuck in a loop. While the probe continued to relay a steady radio signal to its mission control team on Earth over the following months, the signal did not carry any usable data. It was, in effect, a letter sealed inside a working envelope. The transmission infrastructure fully functional, the content gone. Suzanne Dodd, Voyager project manager at NASA's Jet Propulsion Laboratory, said, "It's the most serious issue we've had since I've been the project manager, and it's scary because you lose communication with the spacecraft." She had been project manager since 2010. In that time, there had been anomalies, unexpected behaviors, unexplained data, the accumulated complications of maintaining two of the oldest active spacecraft in history. But this was different. This was not corrupted data from one instrument. This was the entire communication system producing nothing useful across a one-way signal delay of nearly 22.5 hours, with no ability to directly examine the hardware, no technician who could open a panel and inspect a circuit board, no possibility of anything except patience and mathematics, and the slow exchange of signals across a gap that light itself took nearly a day to cross. The team could tell that the spacecraft was still receiving their commands. They could tell it was still executing them, but they could not tell what state it was actually in. The investigation that followed was unlike almost anything else in the history of spacecraft operations, because its constraints were so absolute. Every diagnostic attempt required a command transmission, a 22.5-hour wait for the signal to reach the spacecraft, another 22.5-hour wait for the response to return. A single exchange, question and answer, consumed nearly 2 full days. A wrong hypothesis, acted upon and tested, cost nearly 2 days and produced nothing useful. The team had to be extraordinarily careful about what they asked and how, because asking wrong questions was expensive in ways that no other engineering problem makes time expensive. To understand the system, they had to sift through half a century of documentation written by engineers who had mostly retired or passed away. The Voyager spacecraft were designed and built in the late 1960s and early 1970s. The engineers who made the fundamental architectural decisions, who chose which chips to use, who wrote the original software, who understood the deep structural logic of the flight data subsystem, were in their 20s and 30s at the time of design. They are now in their 70s, 80s, and 90s. Some have died. The knowledge that resided in their direct experience has been preserved, imperfectly, in documentation, in technical manuals and circuit diagrams and memoranda written decades ago for an audience that understood the context implicitly. That documentation must now be decoded by engineers who came to the program long after the spacecraft launched, who are learning the system not from its creators, but from its records. On March 3rd, 2024, nearly 4 months after the anomaly began, mission team engineers saw activity from one section of the FDS that differed from the rest of the computer's unreadable data stream. The new signal was still not in the format used by Voyager 1 when the FDS was working properly, so the team was not initially sure what to make of it. But an engineer with the Deep Space Network was able to decode the new signal and found that it contained a readout of the entire FDS memory. That was the breakthrough. A full readout of the flight data subsystem's memory, 69.63 kilobytes in total, arrived on Earth after 4 months of silence, and with it, the possibility of diagnosis. In March, engineers discovered the cause of the communication problem, a stuck bit in one of the chips comprising part of Voyager's onboard memory. The cause of the stuck bit is a mystery, but it's likely the chip either wore out with age or was hit by a highly energetic particle from a cosmic ray. A single chip in a computer with 69.63 kilobytes of total memory had failed, and that chip happened to contain code critical to the operation of the telemetry modulation unit, the component responsible for packaging and transmitting data. The chip could not be repaired. It could not be replaced. The engineers 24 billion kilometers away had no physical access to it and no means of acquiring any. The chip issue affected code in Voyager 1's flight data subsystem, which rendered the science and engineering data unusable. Engineers were unable to remotely repair the chip, so they created a plan to spread the impacted code across unaffected portions of the flight data subsystem. However, No single location was large enough to accommodate the extra 256 bits. The size of the memory was the biggest challenge in this anomaly, said Spilker. Voyager's computers each have a mere 69.63 kilobytes of memory. Every byte of that memory was already allocated for a purpose. The engineers had to find corners of the existing allocation, procedures that were no longer needed, data modes that had become obsolete as the spacecraft moved further from Earth, that could be repurposed without compromising the systems they were being taken from. Voyager had been programmed with several data modes, the rate at which data is sent back to Earth, because the spacecraft could transmit data much faster when it was closer to Earth. At Jupiter, the spacecraft transmitted data at 115.2 kilobits per second. Now, that rate has slowed to 40 bits per second, and the faster modes could be overwritten. The dead chip's code was broken into pieces, segments small enough to fit into the available corners, and each segment was relocated. It was software surgery performed across 24 billion kilometers of space on a computer architecture that had not been manufactured since the 1970s, using documentation written by engineers, many of whom were no longer alive to consult. The first such fix was transmitted to Voyager, one on April 18, 2024. Once the coding fix for the probe's engineering data was finished, the team had to wait 22.5 hours for the signal to reach the probe, and then another 22.5 hours for the signal to return to Earth. The signal was sent. The team waited. The signal was sent. The Earth rotated. Night fell on the Mojave Desert. Dawn came. The Earth rotated again, almost half a turn. And then Voyager answered. The mission team received the first coherent data about the health and status of Voyager 1's engineering systems on April 20th. While the team was still reviewing the information, everything they had seen so far suggested Voyager 1 was healthy and operating properly. The signal was present. The spacecraft was intact. The conversation had resumed. The relief in the mission team's public communications in the days that followed was palpable but contained. We never know for sure what's going to happen with the Voyagers, but it constantly amazes me when they just keep going, said project manager Suzanne Dodd. We've had many anomalies, and they are getting harder, but we've been fortunate so far to recover from them, and the mission keeps going. They are getting harder. That phrase carries weight that should not be allowed to pass unmarked. Not harder because the engineers are less skilled or the mission less well-resourced, but harder because the spacecraft is older, the systems are more degraded, the documentation is more incomplete, and the margin between each anomaly and mission-ending failure is narrower than it was the time before. Each successful recovery depletes something: a redundant system, a spare memory location, a backup thruster. Younger engineers are coming onto the Voyager team and contributing their knowledge to keep the mission going. But they are learning a system that exists in no other form anywhere on Earth. A system whose original architects are mostly gone, whose design decisions were made 50 years ago, and whose behavior in the interstellar medium cannot be predicted from first principles because no spacecraft has ever been there before. The anomaly of 2023 and 2024 was not an isolated event. It was the most dramatic installment in a long series. Pause here and take a moment to look back at the path we have traced. We began with the RTGs, the nuclear heart of the spacecraft. We followed the power to the transmitter and the signal to the antenna. We traced the signal across 25 billion kilometers of space, through the inverse square law and the interstellar medium, to the cryogenic receivers of the deep space network. We watched the signal being decoded and the data extracted. And now we have arrived at the most human part of the story, the part where the conversation nearly ended, not because of any fundamental physical limit, but because one chip in a 69.63 kilobyte computer failed, and a group of engineers on Earth had to fix it from 24 billion kilometers away using documentation left behind by people who had worked on the problem decades before they were born. That is where the conversation lives. Not in physics. The physics is remorseless and fixed. The conversation lives in engineering, and engineering is human, and human things age. The 2023 to 2024 anomaly was the most serious in recent memory, but the pattern of unexpected failures and creative recoveries extends all the way back through the mission's history, and it reveals something important about both the spacecraft and the people who have kept it alive. Everyone who maintains a 50-year-old spacecraft across a communication link that takes nearly 2 days for a round trip is, in principle, doing something straightforward: monitoring the systems, identifying problems, transmitting corrections. The procedure is well established, the tools are well understood, and the team has been doing it without a significant break for nearly 5 decades. The situation seems like one that should be manageable with sufficient expertise and attention. But here's what almost nobody tells you about maintaining a spacecraft of this age and distance. The knowledge required to do it correctly is not fully captured in any document or database anywhere on Earth. It exists partly in living human memory, and that memory is finite, and it is diminishing. The engineers who designed Voyager's onboard systems understood them at a level of intuitive depth that cannot be fully transmitted through documentation, because documentation captures what was written down, and much of what expert engineers know was never written down. It was understood, assumed, implicit. As those engineers retire or die, what is lost cannot be recovered from the records they left behind. The records capture what? They do not always capture the why or the feel for how the system actually behaves under conditions that its designers chose not to document because they considered those conditions unlikely. When the 2023 anomaly required the team to understand the deep structure of the FDA's memory allocation, they found themselves reading documentation that assumed a level of contextual knowledge that no living person fully possessed. As Linda Spilker observed, with each anomaly, we just learn more about how to work with the spacecraft and are just amazed at the capabilities that the engineers built into it using that 1960s and 70s technology. The amazement is real and well-founded. So is the difficulty. The difficulty compounds with each episode. Consider the sequence of what the Voyager team has confronted and resolved over the years. In 2022, Voyager 1 began transmitting invalid telemetry data from its attitude articulation and control system, the computer responsible for maintaining the spacecraft's orientation. The problem was eventually traced to the AACS, sending its telemetry through a computer that had been non-operational for years, resulting in data corruption. In August 2022, NASA transmitted a command to the AACS to use another computer, which resolved the problem. The solution required knowing that the data was being routed through a dead computer, a piece of information that required reading the system architecture carefully enough to identify a routing path that should not have been active. In 2017, Voyager 1's primary thrusters showed signs of degradation, so engineers switched to another set of thrusters that had originally been used during the spacecraft's planetary encounters. Those thrusters worked, despite having been unused for 37 years. Think carefully about what that means. The backup thrusters had last fired in 1980, when Voyager 1 was in the vicinity of Saturn. They sat dormant through the entire subsequent mission, through the 1980s, the 1990s, the 2000s, the 2010s. while the spacecraft traveled from the outer solar system to interstellar space, enduring cosmic rays and temperature extremes and the slow deterioration of age. When finally called upon in 2017, they fired. The seals had held. The propellant lines had not clogged. The firing mechanisms had not corroded. The engineering decisions made in the late 1960s about materials, tolerances, and redundancy had paid a dividend 37 years after the relevant systems were last used. It worked in 2017. It worked in 2022. It worked through the long nightmare of 2023 and 2024. In May 2025, the team was able to revive the backup thrusters used for roll motion that were unusable since 2004. 21 years of dormancy, and they fired. In October 2024, a different kind of near disaster. The probe turned off its X-band radio transmitter that was used for communications with the DSN. It was caused by the probe's fault protection system that was activated after NASA turned on one of the heaters on October 16th. The fault protection system lowered the transmission rate, but the engineers were able to find the signal. Later, on October 19th, the transmission stopped. The fault protection system was triggered once again and switched to the S-band transmitter, which was previously used in 1981. NASA reported that the team reactivated the X-band transmitter and then resumed collecting data in mid-November. The S-band transmitter, last used in 1981. Voyager had reverted, briefly, to a communication mode not exercised in more than 40 years. And each time the team found a way back. But the resources consumed by each recovery are not replaced. Some thrusters needed to control the attitude of the spacecraft and point its high-gain antenna in the direction of Earth are out of use due to clogging problems in their hydrazine lines. The spacecraft no longer has a backup available for its thruster system, and everything on board is single string, according to Suzanne Dodd. Single string. That phrase keeps returning, and it should. When you hear it in engineering, it means the same thing in every context. The last line of defense is now the only line of defense. If it fails, there is no recovery. The question the mission team lives with, the one that has no definitive answer, only an ongoing renegotiation with probability, is how many more anomalies remain within the range of the soluble. Although Voyager 1 appears to be on the mend from its most recent serious issue, NASA scientists know it won't last forever. Sooner or later, a glitch they can't fix will occur, or the spacecraft's ever-dwindling power supply will run out for good. The RTGs currently provide enough power to maintain the radio, and perhaps one or two instruments. Its radioisotope thermoelectric generators may supply enough electric power to return engineering data until around 2036, though some estimates suggest the timeline could be shorter depending on which instruments remain active and how power margins evolve. That is the current estimate. Estimates vary, and the timeline is sensitive to decisions not yet made about which instruments to shut down and when. We do not know exactly when the conversation will end. We can bound the estimate, but the boundary itself has uncertainty built into it. The spacecraft could fail tomorrow through some unforeseeable cascade of single-string failures. It could survive into the mid-2030s if the power arithmetic works out and no irrecoverable failure occurs. Some researchers believe the RTGs will sustain minimal engineering operations until 2036. Others suggest the timeline could be shorter or longer, depending on how aggressively instruments are powered down. The end is coming. It is not yet here. And everything we can still learn from the spacecraft, it is still learning. It will be decades before a new interstellar science mission provides another opportunity to initiate such fundamentally important and novel lines of research, says Kostas Dialinas, an astrophysicist at the Academy of Athens, and a co-investigator on one of Voyager 1's energetic particle instruments. Decades, not years, not a follow-up mission already in development. Decades before anything else will be in a position to tell us what Voyager is telling us right now. This is the context in which Voyager 1's scientific output must be understood. Not as a legacy mission coasting on past achievements, but as the only instrument in the history of our species that can report directly from interstellar space, and as an instrument whose time is running out. Picture yourself inside the environment Voyager currently occupies, if such a thing can be imagined. You are 172 astronomical units from the Sun, 172 times the distance from Earth to the Sun. The Sun appears as a bright star, clearly the brightest object in the sky, but star-like. No disk, no corona, no sense of dominance over the surrounding field. The solar wind, the constant stream of charged particles flowing outward from the Sun that fills and defines the heliosphere, has ended. You are beyond it. The particles in the environment around you come not from the Sun, but from the galaxy at large. Cosmic rays generated by ancient supernova explosions, interstellar gas that has been drifting through the galactic disk for billions of years. Magnetic fields that thread the space between stellar systems with no particular connection to our own. Nothing else that human beings have built or operated has ever been in this environment. Nothing else has ever measured it directly. The theory of what the interstellar medium looks like at these scales and in this region has been built from remote observations, from the way starlight is reddened and polarized as it travels through interstellar dust, from radio wave dispersion measurements, from models of the galactic magnetic field. But models and remote observations are not the same as an instrument floating in the thing itself, measuring it directly, reporting back in real time. As of 2026, only 2 instruments are operational: the plasma wave subsystem and the magnetometer. The plasma wave subsystem detects oscillations in the charged particles of the surrounding medium. It listens to the electromagnetic voice of the plasma, the natural wave modes that arise in any ionized gas. The magnetometer measures the magnetic field threading the interstellar medium around the spacecraft. Together, these 2 instruments are drawing a portrait of a region of space that has never been characterized by direct measurement before. What they have found is not quite what the models predicted. In 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields in the surrounding interstellar plasma, while its plasma detector measured a rise in plasma density. Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the tenuous interstellar plasma, while its plasma detector measured a rise in plasma density. Similar anomalies had been seen before, but the observations had returned to baseline levels after a period of months. This time was different. The anomalies that began in 2020 did not abate, leading some mission scientists to question whether they originated with the Sun at all. The debate about their origin is ongoing, and it illustrates how much we still do not understand about the boundary region between our solar system and interstellar space. Researchers believe some transient jumps were generated when surges of plasma streaming outward from the Sun smashed against the boundary of the heliosphere, creating swells that reverberate through interstellar space, compressing interstellar plasmas and intensifying their magnetic fields. The source is like a piston, says Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and principal investigator for the magnetometer. On this view, the anomalies are echoes of solar activity. Pressure waves launched by solar eruptions that travel outward through the heliosphere, strike the heliopause, and produce reverberations in the interstellar plasma on the other side. The Sun is not just the center of the solar system. It is a piston driving oscillations in the medium beyond its own boundary. Some researchers find this explanation compelling and consistent with the timing of solar activity events. Others question whether the sustained nature of the 2020 anomalies can be fully explained by solar sources, and suggest that the cause may lie in variations in the local interstellar medium itself. Changes in the density or structure of the gas cloud through which the Sun and its heliosphere are currently traveling. We cannot resolve this question today, and not because the data is insufficient. The question is genuinely at the edge of what the physics allows us to determine with the instruments we have. Stella Ocker, a postdoctoral fellow at Caltech and the Carnegie Observatories, notes that astronomers are good at observing things far off or inside our solar bubble, but struggle to see what's in between. It is surprisingly difficult to observe the interstellar medium that is just outside of our heliosphere. The Voyager spacecraft are sort of on the border of astro and space physics. On the border. That phrase captures something important about Voyager's scientific position. The spacecraft is not simply traveling through a well-characterized environment, dutifully confirming what the theorists predicted. It is in a region that the theorists did not have sufficient data to characterize correctly. Every measurement it returns, every magnetic field reading, every plasma wave signature, every observation of how the density of the interstellar medium changes with distance from the heliopause is a data point in a picture that could not have been drawn any other way. Consider the plasma density measurements as an example. The density of the ionized gas in the interstellar medium has been estimated from remote observations for decades, but those estimates carried significant uncertainty. The theoretical models of how the heliosphere interacts with the interstellar medium, how its shape, its extent, and its boundary conditions depend on the properties of the surrounding medium, are sensitive to that density in ways that change the models substantially. Voyager 1 has been measuring this density directly at its actual location in interstellar space, and the measurements have both confirmed some aspects of the theoretical picture and complicated others. The interstellar medium, it turns out, is not as uniform as some models assumed. Its density varies. Its magnetic field fluctuates. The boundary between the heliosphere and the interstellar medium is not a clean, static surface, but a dynamic, turbulent zone that responds to conditions on both sides. Everything we have learned about the heliosphere's boundary from Voyager, every measurement of the transition zone, every observation of the plasma beyond, has implications for how we understand the boundaries of other stellar systems. Every star with a sufficiently strong stellar wind should have a heliosphere-like bubble around it, defined by the same basic physics. The details, the size, the shape, the turbulence at the boundary, depend on the stellar wind's properties and on the local interstellar medium. Voyager 1's measurements are the first direct characterization of how these parameters combine at one specific stellar system, ours, and they will serve as the empirical anchor for models of stellar boundary regions around other stars. There is no duplicate. There is no parallel mission. There is Voyager 1 in interstellar space with two functioning instruments, a data rate measured in mere tens of bits per second, and an RTG power supply declining at 4 watts per year. The plasma wave subsystem listens. The magnetometer measures. The signal crosses 25 billion kilometers to a cryogenic receiver in the Mojave Desert. And on a screen in a building in Pasadena, California, the universe reports from a place it has never reported from before. That is what the conversation is for. Not the engineering, not the physics, not the design elegance of the radioisotope thermoelectric generators. All of those things are in service of this. A continuous, improbable, diminishing stream of data from the space between the stars, carried home by a 22-watt transmitter and received by the most sensitive scientific telecommunications system human beings have ever built. Every bit of it matters, because when it stops, there will be nothing to replace it for decades. The conversation has always been conditional. From the first moment Voyager 1 departed Earth, the question of how long it could continue to transmit was bound by a finite supply of nuclear fuel and an irreversible process of thermocouple degradation. The engineers who built the spacecraft knew this. The mission planners who designed the extended mission knew this. The scientists who have interpreted the data for 50 years have known this. The end of the conversation has always been somewhere on the horizon. Not an if, but a when. What changes now is that the horizon has come close enough to see clearly. The current power situation is tight in ways that have no precedent in the mission's earlier decades. The RTGs are generating less than half of what they produced at launch. Each spacecraft now produces less than half its original electrical power, leaving engineers with razor-thin margins between keeping the radio alive and tripping the undervoltage fault protection system. The allocation of that remaining power is managed with an austerity that has no parallel in civilian engineering. The transmitter claims the largest share, because without the transmitter, nothing else matters. The attitude control systems claim their portion. The onboard computers require their allocation. After these mandatory draws on the budget, what remains for science instruments is vanishingly small. Enough, as of 2026, for 2 instruments and nothing more. Its radioisotope thermoelectric generators may supply enough electric power to return engineering data until 2036. That estimate is not a guarantee. It is a calculation based on current power trends and current instrument configurations, updated periodically as the actual decline rate is measured against the projected rate. Some mission scientists are more optimistic about the timeline. Others are more cautious, noting that unexpected power draws, like the one that triggered the fault protection system in October 2024, can consume reserve margins that were not included in the baseline projections. What no researcher disputes is the direction. The budget contracts, the allocations grow harder, and at some point the transmitter itself will not have enough power to maintain its output. The fault protection system, the onboard software that monitors critical parameters and takes automatic corrective action when they fall outside safe bounds, is the last barrier between a low-power event and catastrophic mission loss. When the voltage available to the transmitter drops below threshold, the fault protection responds. It reduces data rates. It shuts off non-critical systems. In extremis, it switches to backup transmitters. What it cannot do is create power that does not exist. In October 2024, the probe turned off its X-band radio transmitter. It was caused by the probe's fault protection system, which was activated after NASA turned on one of the heaters on October 16th. The fault protection system lowered the transmission rate, but the engineers were able to find the signal. Later, on October 19th, the transmission stopped. The fault protection system was triggered once again and switched to the S-band transmitter, which was previously used in 1981. NASA reported that the team reactivated the X-band transmitter and then resumed collecting data in mid-November. The transmitter last used in 1981. Voyager reached back 43 years to a backup that had been completely dormant since before most of the engineers currently working on the mission were born. And it worked. But the incident revealed something the mission team already understood, and the rest of us rarely think about. The power margin is now so narrow that routine operations, turning on a heater, can trigger emergency responses. The spacecraft is operating so close to its limits that the boundary between normal function and crisis can be crossed by a single watt of unplanned demand. The progressive shutdowns have been relentless. Cameras went first years ago. Then came the heaters for various instruments, then the instruments themselves. One by one, each decision made with the full understanding that it was irreversible. As of late April 2026, 2 instruments remain in operation. 2 instruments. And the radio. The radio runs, or the mission ends. That is the entire calculus. Every decision the mission team has made for the past decade has been made in service of one thing: keeping the radio alive long enough to transmit what the 2 remaining instruments still have to say. 4 watts per year, 48 years. The math is not complex. The implications are. There is a second kind of communication aboard Voyager 1, one that does not depend on the RTGs or the transmitter or the deep space network. It requires none of the infrastructure we have spent these past hours tracing. It will outlast every link in the chain that keeps us in contact today, and it will keep traveling long after the last signal has been received and decoded and archived. Hold in your mind the image of a disk, gold-plated copper, 12 inches in diameter, mounted to the exterior of the spacecraft and exposed to whatever the interstellar medium brings. The Golden Record was designed and assembled in 1977 under the direction of a committee chaired by the astronomer Carl Sagan, with Anne Druyan serving as creative director. The spacecraft carries a golden phonograph record containing sounds, music, and images representing life on Earth, intended as a message to any civilization that might one day encounter it. The medium was chosen deliberately. A groove-encoded analog disc can be decoded from its physical structure alone, without reference to any specific technology standard, by any intelligence capable of understanding that a groove encodes a wave. The record contains 115 images representing mathematics, human anatomy, landscapes, the solar system, and other aspects of life on Earth. It carries greetings in 55 human languages and one from humpback whales. It contains 90 minutes of music drawn from dozens of cultures across human history. It carries sounds, ocean waves, wind, thunder, birds in flight, the heartbeat of a mother carrying a child not yet born. The record is not a technical document. It is an introduction. It says, in the only language available across truly vast distances, we existed, we were like this, and we sent this piece of ourselves outward because something in us insisted on doing so. The record will almost certainly never be received by the intelligence for whom it was intended. The distances involved make any encounter between Voyager and an inhabited system a matter of cosmic chance rather than design. Voyager 1's trajectory carries it in the direction of the constellation Ophiuchus, and in approximately 40,000 years, it will pass within about 1.7 light-years of a red dwarf star called Gliese 445 in the constellation Camelopardalis. Not through the system, 1.6 light-years is a third of the distance between our Sun and the nearest known star. A pass at that distance would be undetectable from Gliese 445's surface, even if anyone were watching. After that, Voyager 1 will continue outward into the galaxy, its trajectory bent imperceptibly by the gravitational fields of passing stars over millions of years, on a path that diverges beyond any predictability. In 1 billion years, it will still be moving. In 5 billion years, when the Sun expands into a red giant and the inner solar system is consumed, The spacecraft will be somewhere in the Milky Way, its origin forgotten by any intelligence that might notice it, if any intelligence remains to notice anything at all. And the record will be intact. Gold does not corrode in the interstellar medium. The grooves encoding the sounds of Earth in 1977, ocean waves, birdsong, a mother's heartbeat, 90 minutes of music, will be physically legible for an incomprehensibly long time. The communication chain we have traced, the RTGs and the transmitter and the 70-meter dishes and the cryogenic amplifiers, will end within a decade. The record will not end for something approaching 1 billion years. The engineered channel is the temporary one. The analog disc, pressed in a California studio in 1977, is the permanent one. When the last bit of Voyager data is decoded in the Signal Processing Center at JPL, the spacecraft will not have ended. It will simply have fallen silent. The record will keep going. The sounds of Earth will keep traveling at 17 kilometers per second through the dark between the stars, carrying its introduction to an audience that may or may not exist, across distances that make the word distance feel inadequate. The record will outlast the conversation by approximately the age of the universe. Now take the longest possible view of where Voyager 1 is going, not in months or years, but in timescales the universe uses for its own accounting. At 17 kilometers per second, the spacecraft covers approximately 536 million kilometers per year. A single light year, the distance light travels in 1 year, is approximately 9.46 trillion kilometers. At Voyager's current pace, traveling 1 full light year from its starting point would take roughly 17,500 years. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, and Voyager is not traveling toward it. That comparison is illustrative, not literal. To reach Proxima Centauri from here would take approximately 73,000 years at Voyager's speed. The spacecraft is, in other words, moving at a speed that feels extraordinary by every human standard, and is, by the standards of interstellar travel, nearly motionless. The galaxy is enormous beyond any frame of reference that works for human minds, and Voyager is crossing it at the speed of a very slow wind. In 40,000 years, it will have moved 1.6 light-years from its closest approach to Gliese 445. In 1 million years, it will have traveled roughly 17 light-years from its origin, a distance that would carry it to perhaps a handful of neighboring stellar systems, none of which it will pass through closely enough for any interaction. The spacecraft will outlast the civilization that built it. This is almost certain. It will still be traveling when the Sun leaves the main sequence. It will still be traveling when the last star in the Milky Way exhausts its fuel and goes dark. In the deepest accessible timescale, Voyager 1 becomes something other than a human artifact. It becomes a feature of galactic geography, a piece of processed metal and decayed plutonium, traveling through the dark, long since silent, long since forgotten, carrying in its grooves the sounds of a world that built it and sent it away. But right now, in 2026, it is still ours. The signal still arrives. The cryogenic receivers at Goldstone and Canberra and Madrid still listen. The engineers at JPL still decode the data. The plasma wave readings and the magnetic field measurements still appear on screens, number by number, bit by bit, a slow trickle from 25 billion kilometers away. Take stock of the whole picture now, before the next turn. We began with 22 watts and a question. How does a signal that faint cross 25 billion kilometers and arrive as coherent data? And the answer, after tracing every link in the chain, is this. It arrives because every component of an extraordinarily complex, aging, fragile, irreplaceable system has continued to function well enough, for long enough, against probabilities that no reasonable design specification would have guaranteed. It arrives because of plutonium synthesized in December 1940 and thermoelectric principles discovered in 1821, and antenna designs refined over decades, and cryogenic amplifier technologies developed through patient and unglamorous engineering. It arrives because DSS-43 in Canberra was restored in time, and because the fault protection system was overridden in October 2024, and because a team of engineers read documentation written by people who are now mostly gone and found the code that a failing chip had scrambled and moved it, bit by careful bit, into the spaces that remained. And it arrives because year after year, for nearly 50 years, someone has kept the listening infrastructure operational, because someone has chosen to. Now consider that more carefully, because it is here that the entire story turns. What is it, exactly, that we have been maintaining for 50 years? Is it a spacecraft? The spacecraft is in interstellar space, unreachable, unrepairable, opaque to any form of direct inspection. In what sense do we maintain something we cannot touch, cannot see, cannot confirm with our own senses, except through the signal it sends back? Is it a signal? The signal propagates at the speed of light and requires no human action to continue traveling once it has been launched. We maintain the infrastructure to receive it, but the signal itself is indifferent to whether we are listening. Is it a measurement? The data arriving at 40 bits per second represents real conditions in the interstellar medium, real oscillations of plasma, real readings from real instruments attached to a real machine. But those conditions exist, whether or not we are receiving the data. The interstellar magnetic field does not care whether the number describing it lands successfully on a screen in Pasadena. What we have been maintaining, and what becomes clear only when you hold the full picture in your mind at once, is the connection itself, not the hardware at either end, but the link between them. The continuously renewed commitment that the thing at the far end of the chain is worth reaching. Consider what maintaining that commitment actually required. It required 3 complexes of giant radio antennas on 3 continents to be kept in operational condition for more than 6 decades. It required a succession of engineers, each generation inheriting a problem the previous generation had left incompletely solved, to keep finding ways to extend a mission that had already outlasted its design life by a factor of nearly 10. It required that the scientific community repeatedly and successfully argued for the resources to maintain the receiving infrastructure, against competing claims from newer missions with fresher data and louder advocates. It required that in no year since 1977 did anyone make the final determination that the conversation was no longer worth having. It worked in 1979 when Voyager reached Jupiter and the DSN was still young. It worked in 1989 when Voyager 2 flew past Neptune and the 70-meter dishes were expanded for the occasion. It worked in 2012 when Voyager 1 crossed the heliopause and entered interstellar space, becoming the first human-made object to do so. It worked in 2017 when backup thrusters dormant for 37 years fired correctly on command. It worked in 2022 when invalid telemetry was traced to a routing path through a dead computer. It worked in 2024 when a failed memory chip was repaired across 24 billion kilometers, using code moved into corners of 69.63 kilobytes of onboard memory, by engineers reading documentation written by people who had mostly retired or died. It worked every time. And here is where the story inverts itself. in the way that genuine understanding sometimes inverts the question that led you to it. We asked, how are we still in contact with Voyager 1? The engineering answer traces the signal from the decaying plutonium through the transmitter, through the high-gain antenna, through 25 billion kilometers of interstellar medium, through the cryogenic receiver, through the phase-locked decoder to the screen in the signal processing center. That answer is real. It is necessary. It is, in its own right, extraordinary. But there is a second answer, and it is the one that makes the first answer possible. We are still in contact with Voyager 1 because we chose to be. Not once, in 1977, when the spacecraft launched. Continuously, every year since, in every budget cycle and every staffing decision, and every maintenance contract for every dish on every continent. The engineering made contact possible. The commitment made it actual. Once you see that, something fundamental shifts in the picture. You look back at the RTGs and see not just nuclear batteries, but a 50-year bet that someone would still be listening when the heat finally ran low. You look at the cryogenic amplifiers and see not just sensitive electronics, but the maintained infrastructure of an intention, the intention to hear what comes back from the edge of the known. You look at the three complexes spaced 120 degrees apart around the globe, at Goldstone in the Mojave Desert, and Robledo de Chavela in the Spanish Hills, and the rolling country outside Canberra. And you see not just antennas, but a sustained, distributed, multi-generational act of listening. What if the DSN had not been maintained? What if, in 1992, or in 2003, or in 2015, the budget had been cut and the listening had stopped? The spacecraft would still be out there. The signal would still be traveling toward Earth. But there would be no one to receive it. The interstellar medium's magnetic field would be oscillating and compressing and varying in ways that no instrument on Earth would ever measure. The plasma density readings that allow researchers to characterize the structure of the local interstellar environment would simply not exist. We cannot know what those unheard measurements would have told us, because we cannot trace the absence of knowledge. It leaves no record of what it prevented us from learning. We cannot know, even now, how many more recoveries remain within the achievable range. We cannot know whether the anomaly that finally ends the mission will be a sudden catastrophic failure or a slow arithmetic defeat as the power budget finally fails to close. We cannot know what the last measurement will contain, whether it will capture something scientifically remarkable in its final moment, or whether it will be a routine data packet, indistinguishable from the millions that preceded it, except that no packet will follow. What does it mean that the most recent direct measurements of the interstellar medium come from instruments designed before the personal computer existed, running on a 69.63 kilobyte computer, transmitting 40 bits per second to a dish that was a 64-meter antenna when John F. Kennedy was still alive? What does it mean that the conversation, with all its fragility and all its age and all its single-string precariousness, is still happening? What does it mean for the people who have kept it alive, the engineers who wrote the documentation their successors are now reading, in order to understand decisions made by people who can no longer explain themselves? What kind of civilization maintains a conversation for 50 years with something it can never visit, confirm with its own eyes, or retrieve? What kind of civilization, having maintained that conversation for 50 years, would choose to let it fall silent before physics demands it? The engineering answer is complete. Every link in the chain has been traced, from the plutonium Glenn Seaborg synthesized in December 1940 to the phase-locked decoder in the signal processing center at JPL. The physics is fixed. Inverse square law, 40 bits per second. Cryogenic noise floors, 87.7-year half-life. These things are not negotiable. The human answer is not complete, because human answers never are. They are ongoing. They are renewed or abandoned by each generation in turn. The conversation with Voyager 1 is, on one level, a triumph of physics and engineering that took half a century to accumulate its full weight. On another level, it is a choice that a succession of human beings has kept making, quietly and without fanfare, for longer than most people alive today have been alive. That is what is extraordinary. Not the signal, not the dish, not the RTGs, or the cryogenic amplifiers, or the 312 silicon-germanium thermoelectric couples that convert heat into the power that drives the transmitter. The fact that someone has always been there to listen. Stand in the signal processing center at JPL on a quiet weeknight, not during a crisis, not during a thrilling first encounter with a new planetary body, but on an ordinary Tuesday when the work is routine, and the word routine carries its full weight. Routine meaning what happens today has happened yesterday and will happen tomorrow and will keep happening for as long as the power holds. The room is lit by screens. Engineers at their consoles track the incoming signal from the Deep Space Network, from whichever of the three complexes currently has Voyager 1 above its horizon. At this moment, it might be Goldstone, the desert complex in the Mojave, where the night sky carries almost no radio interference, where the dish is turning so slowly against the stars that the motion is perceptible only if you watch for a very long time. The dish is pointing at a location in the sky where, if you could see radio waves, there would be nothing distinguishable, just the darkness between stars, just the absence of objects that characterizes the interstellar void. And yet, the receiver at the dish's focus is registering something. It is measuring a quantity in billionths of a billionth of a watt. The cryogenic duo surrounding the front-end amplifier is keeping the electronics at roughly 15 degrees above absolute zero. And at that temperature, the thermal noise has been suppressed enough that Voyager's signal stands above it. Barely, but above it. The phase-locked loop has found the carrier frequency and locked on. The error-correcting decoder is running. Numbers are appearing on screens. The numbers are magnetic field readings from interstellar space. There is something in this scene that resists casual description, because the scale of what it represents does not fit into the ordinary language of work. An engineer sits at a desk in a building in Pasadena, California. In front of them, a screen displays numbers that describe conditions in an environment no human being has ever visited, that no instrument before this one has ever measured, that no subsequent mission will reach for decades. Those numbers arrived 20 minutes ago, or 40, depending on when this particular reading was captured. After traveling at the speed of light for more than 23 hours from a machine the size of a small car, moving through the space between the stars at 17 kilometers per second, the engineer reads the number. They compare it to the expected range. They note it in the log. Then the next number arrives, and the one after that. 160 per second, patient and relentless. This is what the entire chain is for. Not the crises, not the dramatic recoveries, not the anomaly investigations that consume months of careful work, though all of those things have been necessary to keep this moment possible. The chain is for this. The daily, quiet accumulation of data from a place no one else can reach, delivered to a room in California in a slow trickle of bits, hour after hour, day after day, while the spacecraft that sends it keeps moving outward at a speed that is simultaneously extraordinary and cosmically slow. The signal left Voyager's antenna while most of North America was sleeping. It traveled through the tenuous plasma of the local interstellar medium, through the faint magnetic fields threading the space between stars. It weakened second by second as the sphere of its propagation expanded. It arrived at the upper atmosphere of Earth, carrying a power smaller than anything a human nerve could detect. The cryogenic receiver caught it. The amplifiers lifted it from the noise. The decoders read the phase shifts. The error correction cleaned the data stream. And now it is a number on a screen, in a room where the lights are on, and someone has left a coffee cup on the corner of a desk. The RTGs are still warm. Somewhere on a boom extending from Voyager's main body, 3 cylindrical canisters of plutonium-238 oxide are releasing their steady, slow heat, the same heat they have been releasing since September 5, 1977. The decay continues and is unstoppable, and is entirely indifferent to the mission's needs. Each sphere of pressed plutonium dioxide is shedding alpha particles at its characteristic rate. The same rate it would shed them if the spacecraft had never launched, if it was sitting in a laboratory, if it were at the bottom of an ocean. The physics of radioactive decay does not know it is powering a mission. It does not know anything. It simply continues, as it has for 48 years, as it will for decades more, slowly and inevitably reducing the thermal output that flows through 312 silicon-germanium junctions and emerges as the electricity that keeps the transmitter alive. The signal travels. It travels. It travels. And in a desert in California, or in the hills outside Madrid at Robledo de Chavela, or in the rolling country near Canberra, a dish turns slowly on its hydrostatic bearing, floating on a film of pressurized oil, and listens. What is it like to work on this mission? What is the texture of that awareness on an ordinary Tuesday when no anomaly is developing and no crisis is looming, and the data is coming in cleanly at 40 bits per second? The people who work on Voyager have been inheriting the mission from one another for nearly 50 years. The engineers who designed it are mostly gone. Those who operated it through the planetary encounters have mostly retired. The people in the Signal Processing Center today learned the mission from people who learned it from people who were there at the beginning. They are the latest link in a human chain that started before many of them were born, and that will end sometime in the next decade or so, while they are still working. There is something particular about working on a mission with a known and approaching end. The energy of a new mission is one thing. The building, the planning, the launch, the first data, the first extraordinary images. The energy of a mission in its final years is different, more weighted, more deliberate, more conscious of what each data packet represents. Every measurement from the 2 remaining instruments is one that cannot be repeated. Every bit of magnetic field data from the local interstellar medium is a first and last. First, because no instrument has ever made this measurement from this position before. Last, because no instrument will be in position to continue it when Voyager falls silent. The engineers carry this quietly. The spacecraft keeps going. 17 kilometers per second, outward in a direction that takes it further from Earth with each passing second. The golden record travels with it in silence. No power required, no maintenance needed, no antenna pointed homeward. It is simply along for the journey, a disk of gold-plated copper carrying the sounds of a world that recedes at some 17 kilometers per second, its grooves encoding waves that will outlast the civilization that pressed them. The signal arrives. The number appears. The engineer notes it. The next number arrives. This has been happening every day for 48 years. It will keep happening, all things being equal, for a few years more. Stay with that for a moment, before the next turn. The dishes rotate, the receivers listen, the numbers appear on the screen. And somewhere, 25 billion kilometers away, the spacecraft keeps going. To understand what the Voyager program actually is, not as an engineering project or a scientific mission, but as a human act, you need to place it in the longest possible context. Not the history of space exploration, which is barely 70 years old. The history of the impulse that drives it. The impulse to project communication, presence, and identity beyond the reach of the human body. That impulse is ancient. It predates writing. It is so old and so consistent across cultures and eras that it begins to look less like a feature of any particular civilization and more like a feature of the species itself. Consider the earliest long-distance communication systems we know of. In ancient Greece, chain relay systems of hilltop signal fires could carry a simple message, not words, but the fact of an event, across hundreds of kilometers in a single night, faster than any human messenger could travel. The playwright Aeschylus, writing in 458 BCE, described exactly such a system in his tragedy Agamemnon. A chain of signal fires stretching from the burning city of Troy across the Aegean Sea and the mountains of northern Greece to the palace at Argos, carrying the news of Troy's fall across roughly 1,500 kilometers in a single night. Whether or not Aeschylus's specific chain is historically accurate, the technology it depicts was real, and it represents something important. The first recognizable understanding that information could travel faster than human beings, and that infrastructure could be built to enable that faster travel. From hilltop fires, the chains stretched forward through centuries. In 1794, the French engineer Claude Chappe built the world's first practical optical telegraph, a network of towers, each one visible from the next, using jointed mechanical arms to encode letters. Within a decade, France had connected Paris to its major cities through relay stations that could carry a message from the capital to the southern coast in approximately 20 minutes. Chappe's network operated for more than 50 years, until electricity made the towers obsolete. Not because the idea was wrong, but because a better carrier had been found. The electric telegraph replaced the towers. In 1866, Cyrus Field completed the first permanent transatlantic telegraph cable, running from Valentia Island off the coast of Ireland to Heart's Content in Newfoundland. For the first time in history, a message could cross the Atlantic Ocean in minutes, rather than the 10 to 12 days a ship required. The sense of separation between the old world and the new, a sense that had been built into the experience of travel, into the experience of waiting, into the very rhythm of international relations, collapsed. Distance remained. Duration vanished. In 1901, Guglielmo Marconi transmitted the first radio signal across the Atlantic, from Poldhu on the coast of Cornwall, England, to Signal Hill in St. John's, Newfoundland. Many physicists had argued it was impossible. The Earth's curvature should have blocked any line-of-sight radio transmission. They were right about the geometry and wrong about the outcome, because the signal bounced off the ionosphere, a conducting layer in the upper atmosphere whose existence was itself unknown until the radio experiment made it inferable. Marconi had demonstrated that the atmosphere contained a natural relay system that no one had known to look for, and that the physics of communication could exceed the physics anyone had yet measured. In 1931 and 1932, Carl Jansky at Bell Telephone Laboratories in New Jersey was investigating sources of radio interference when he discovered that one persistent source of static in his receiver was not terrestrial in origin. After careful analysis of its timing and direction, he concluded that it was coming from the center of the Milky Way. He had not built an astronomical instrument. He had built a communications receiver, and the universe had spoken through it. Jansky had detected radio waves from tens of thousands of light years away, electromagnetic radiation generated by natural astrophysical processes in the galactic core, arriving at his antenna with enough intensity to be measured and tracked. The field he inadvertently founded, radio astronomy, eventually produced the technology tradition from which the Deep Space Network directly descends. The 70-meter dishes at Goldstone and Canberra and Robledo de Chavela are, in a very real sense, Jansky's heirs. From hilltop fires in ancient Greece, to mechanical relay towers across Napoleonic France, to copper cables along the Atlantic floor, to Marconi's ionospheric bounce, to Jansky's accidental discovery of the galaxy's voice, to the Deep Space Network and the cryogenic receiver listening for a 22-watt signal from 25 billion kilometers away, 2.5 millennia. The same impulse, scaled up by orders of magnitude with each technological generation, pointed further and further outward, demanding more and more of whatever sensitivity the current era's technology could provide. Voyager 1 is not an anomaly in this history. It is the current expression of a pattern older than recorded civilization. But it is also something more than a data point in the communications technology timeline. Because no previous communication across great distances was a communication with something that had never been there before. Chapez towers carried messages between cities that had always existed. The transatlantic cable connected civilizations that had been trading and fighting for centuries. Marconi's radio waves bounced off a layer of the atmosphere that had been in place for billions of years before any human being thought to look for it. Even the first radar contact with the moon, made in 1946 by the US Army Signal Corps at Fort Monmouth, New Jersey, when a radar pulse was sent toward the moon and its echo received 2.5 seconds later, was a signal exchange with a body that had been orbiting Earth since long before life existed on its surface. Voyager 1 crossed into an environment that no object of human origin had ever entered. When the spacecraft passed through the heliopause in August 2012, it was not visiting a known place. It was creating the category of known for an environment that had previously existed only in theory and in remote inference. Every measurement since then has been a first. Every data packet has described conditions that had never been described by any instrument anywhere. The interstellar medium in the vicinity of our solar system is no longer entirely unknown, because for 14 years, an instrument has been floating in it, measuring it directly, reporting home at 40 bits per second. On February 14, 1990, at the request of astronomer Carl Sagan, the Voyager 1 team commanded the spacecraft to turn its cameras back toward the inner solar system and photograph Earth from approximately 6 billion kilometers away. The resulting image shows our planet as a pale blue dot, less than a single pixel wide. Suspended in a scattered beam of sunlight, one point of dim light among 60 photographs, taken in a portrait of the solar systems seen from outside. In that image, every human being who has ever lived occupies a fraction of that pixel. Every war ever fought, every civilization ever built, every love ever declared or withheld, every piece of music ever composed, every injustice ever committed, and every act of courage in response, all of it on a mote of dust suspended in a sunbeam, orbiting an unremarkable star in the outer arm of an average galaxy. That image was the last thing Voyager 1's cameras ever recorded. After those photographs were transmitted, the cameras were shut down permanently to conserve power. The last thing the spacecraft ever photographed was the world that built it, seen from so far away that it was barely distinguishable from the surrounding darkness. The cameras went dark in 1990. The spacecraft has not looked back since. It cannot. There is no power for it, no operational reason, no purpose in turning. Voyager 1 faces outward as it has for nearly 5 decades, its antenna pointed at the pale blue dot it can no longer photograph, and transmits. And we receive. The signal that arrives at the DSN dishes in 2026 carries the same essential meaning it has always carried, even though the content has shifted from planetary images to interstellar plasma readings. It means the chain is intact. I am here. The distance has not been won yet. Every data packet is a refusal to dissolve into the interstellar medium without accounting for what the instruments found there. A refusal to go silent before the power fails. A refusal sustained every single day by the people maintaining the receiving infrastructure to stop listening before physics forces them to. From the hilltop signal fires of ancient Greece to the cryogenic receiver in the Mojave Desert, the impulse is the same. The scale is incomprehensibly larger. What has changed between Aeschylus's chain of fires and the deep space network is not the desire to reach further than the human body can reach. It is only the technology that determines how far further can mean. We have reached 25 billion kilometers and counting. They built signal fires on mountaintops. They built towers with jointed mechanical arms. They laid copper cables along the floor of the Atlantic. They built radio towers and listened to the galaxy's hiss and turned that accident into a science, and that science into an infrastructure. And eventually, they built 3 giant dishes in 3 deserts on 3 continents, cooled their electronics to 15 degrees above absolute zero, and pointed everything at the edge of the solar system. And what comes back at 160 bits per second is worth more than the effort required to receive it. Not because of what the measurements contain, though what they contain is scientifically irreplaceable, but because of what the act of receiving them represents in the ledger of what our species has chosen to do with the brief interval it occupies. We built this. We maintain it, not because it is efficient or cheap or straightforward, but because the thing at the far end of the chain is worth reaching, and because there is something in us, something very old and very persistent, that refuses to accept that the edge of the known is the edge of the possible. The signal arrives. The number appears on the screen. The engineer notes it in the log. And somewhere in the interstellar medium, a machine the size of a small car carries the sounds of a vanishing world outward into the dark, keeping its antenna pointed backward at the pale blue dot, transmitting. Here is what we have traced in the time since we began. We began with a spacecraft that left Earth in 1977 on a trajectory no human being alive today will see completed. We asked the simplest possible question about it. How are we still in contact? And the answer, it turned out, required following a chain that runs from atomic physics to human philosophy, from the discovery of a thermoelectric principle in 1821 to a cryogenic receiver in the Mojave Desert, from a spacecraft the size of a small car to the longest sustained act of listening in human history. The chain begins with heat. Plutonium-238, first synthesized in December 1940 by Glenn Seaborg and his colleagues, decays inside 3 generators mounted on a boom extending from Voyager's main body. The heat of that decay flows through 312 silicon-germanium junctions, each one exploiting the Seebeck effect, discovered in 1821 and first built into a working space power system in 1954 by Ken Jordan and John Burden at the Mound Laboratory in Ohio. The heat becomes electricity. The electricity reaches the transmitter. The transmitter converts that electricity into a radio wave at 8.4 gigahertz, and the 3.7-meter high-gain antenna concentrates that wave into a beam aimed at a planet 25 billion kilometers away. The beam leaves the spacecraft at the speed of light. It travels for more than 23 hours through the interstellar medium, through the tenuous plasma, through the oscillating magnetic fields, through the faint scintillations that researchers like Stella Ocker use to characterize the density of the environment the spacecraft crosses. By the time the signal arrives at Earth, it carries a power measured in billionths of a watt, diminished by the inverse square law across a distance that makes every other communication link in human history look trivially short. 3 complexes of giant radio antennas receive it: at Goldstone in the Mojave Desert, 60 kilometers north of Basto, California; at Robledo de Chavela in Spain, in the hills west of Madrid; near Canberra, in the rolling country of the Australian Capital Territory, spaced 120 degrees apart around the globe, so that as the Earth rotates, at least one of them is always listening. Hand off, hand off, hand off. A relay that has been running without interruption since Christmas Eve 1963. The 70-meter dishes float on hydrostatic bearings, 6 million pounds of moving structure pointing at a precision of 0.005 degrees, at a spacecraft they cannot see. The cryogenic receivers suppress their own thermal noise to the point where Voyager's signal stands above it, barely, but above it. The phase-locked loops track the carrier. The error-correcting codes clean the data. 160 bits per second arrive on a screen in the Signal Processing Center at JPL. And once a year, or more often than that, something goes wrong, and a team of engineers reads through documentation written by people who have mostly retired or died, and finds a way to keep the chain intact for another year. In 2017, backup thrusters unused for 37 years fired correctly on command. In 2022, invalid telemetry was traced to a routing path through a computer that had not been operational for years. In late 2023, the flight data system fell into a repeating loop, and the data stream became unreadable. Engineers spent 5 months tracing the failure, moving code into the spare corners of 69.63 kilobytes of memory, and transmitted the fix across 24 billion kilometers. They waited 22.5 hours for the signal to arrive. They waited another 22.5 hours for the response. On April 20th, 2024, coherent data appeared on the screen, and the mission continued. The chain held. That is the engineering story, and it is extraordinary. But the engineering story, as we found, is not the whole story. The whole story includes the 50-year commitment that made the engineering story possible. The sustained human decision, renewed every year in every budget cycle and every staffing plan and every maintenance contract, that the thing at the far end of the chain was worth reaching. The succession of people, Gary Flandreau calculating orbital trajectories in 1965, Edward Stone serving as project scientist for more than 50 years, Suzanne Dodd managing the mission through its most serious modern crises, and all the engineers whose names are in the documentation their successors now read, who kept believing that the conversation was worth the cost of continuing it. The physics was fixed. The human commitment was not. The physics made contact possible. The commitment made it actual. Consider what Voyager 1 has become in the 48 years since it left Earth. It began as a mission designed to last 5 years, carrying 11 instruments on a journey to Jupiter and Saturn. It is now the furthest human-made object in existence, carrying 2 functioning instruments through the interstellar medium, reporting on an environment no object of human origin had ever entered before it, at a data rate of 40 bits per second, powered by 22 watts from decaying plutonium. The last photograph it ever took, in 1990, was of the world that built it. A pale blue dot less than a pixel wide, suspended in a beam of scattered sunlight, everything we have ever been, barely distinguishable from the surrounding dark. The cameras shut down after that. The spacecraft has not looked back since. It faces outward, antenna aimed at home, transmitting. And somewhere in the interstellar medium, the golden record travels with it. Gold-plated copper, 12 inches in diameter, carrying ocean waves and birdsong, and 90 minutes of music and the sounds of a world in 1977, encoding all of it in grooves that will outlast the civilization that pressed them, traveling at 17 kilometers per second through the dark between the stars toward a close passage with a red dwarf star called Gliese 445 in roughly 40,000 years, a passage so distant that no one there could detect it even if anyone were watching. The record will keep traveling long after the last signal has been decoded and archived at JPL. Long after the last engineer who worked on the mission has retired. Long after the last person who ever heard of Voyager 1 has lived and died. The sounds of Earth in 1977 will keep moving through the galaxy for a time measured in billions of years. The chain we built will last a decade or so more. The record we attached to the spacecraft will last something approaching the age of the universe. What is the right response to that? What do you do with the knowledge that the most durable thing human beings have ever sent into the cosmos is not a piece of technology, but an introduction, a greeting, a collection of sounds and images saying, "We existed, we were like this, and we were curious enough about what was out there that we sent this piece of ourselves to find it." There is melancholy in it, because the conversation is ending and nothing will replace it for decades, and the world the record describes is already 48 years in the past, and the spacecraft carrying it will be silent before most of the people who care about it today have finished their careers. The approaching silence is real. It is not a metaphor, and it is not far away. But there is something else in it too. Something that sits alongside the melancholy without displacing it. There is the fact that it happened at all. That in 1977, at a moment when the alignment of the outer planets made the journey possible for the first time in 176 years, human beings built 2 machines and pointed them outward. And the machines worked, and they are still working. And the chain of people who have kept them working has held without a fatal break for nearly 5 decades. That the impulse to reach further than the body can reach, the same impulse that puts signal fires on Greek hilltops and mechanical telegraph towers across Napoleonic France and copper cables along the Atlantic floor, found its fullest expression yet in a 722 kilogram spacecraft with 69.63 kilobytes of memory and a 22-watt transmitter, sent into the dark with a gold record attached, and has been received and sustained and honored every day since. The signal that leaves Voyager 1 each day and crosses 25 billion kilometers to a cryogenic receiver in the California desert is not ordinary. It never was. It only seemed ordinary from a distance, before you followed the chain. Before you understood what it takes for 22 watts to become a number on a screen. The plutonium, and the thermocouples, and the Seebeck junctions, and the antenna, and the inverse square law, and the interstellar medium, and the 70-meter dishes, and the hydrostatic bearings, and the cryogenic dewars, and the phase-locked loops, and the error-correcting codes, and the engineering team reading 50-year-old documentation, and the decisions made in budget rooms, and the maintenance schedules for dishes that weigh 6 million pounds, and the 48 years of unbroken commitment to listening. Once you know all of that, the signal is no longer ordinary. It is the most improbable regular event on Earth. Every day it arrives. Every day someone reads it. Every day the chain holds. For a few years more, it will keep arriving. And then, on some day that cannot be predicted from here, it will not. The power budget will fail to close, or a thruster will clog, and the antenna will drift, or a chip will fail in a way that the remaining memory cannot accommodate. The chain will end, not with any ceremony, but with the quiet cessation of a signal that had been expected and will simply not come. An engineer will note the absence in the log. The mission will be officially concluded. The dishes will turn to other targets, and Voyager 1 will keep going. 17 kilometers per second, outward into the dark. The record is still attached. The antenna is still pointing at a home it can no longer reach. We sent it. We followed it for nearly 50 years. We kept the chain intact through every crisis and every failure and every near miss, because the conversation was worth having, and because the people who worked on the mission believed that and passed that belief to the people who came after them, who will pass it to the people who come after them, right up until the last signal arrives and the log is closed. If this changed how you think about what it means to be in contact with something, about what distance is and what listening costs, and what we choose to reach for and why, then the time was well spent. Thank you for staying. The universe is stranger and more demanding and more beautiful than the textbook answer suggests. And the people who spend their careers receiving 22 watts from 25 billion kilometers away are proof of something worth knowing about the species you belong to. The signal is still arriving. Somewhere in the California desert, a dish is turning. The number is on the screen. For now, the chain holds.